So this is non-imperative network programming. Sorry for the late start. I'm Mindy Preston. I'm going to start off with a couple of disclaimers. Views expressed are my own. They're not anyone else's. No one bribed me enough to come up and give their opinion instead of mine. And also, I'm new to functional programming. There are definitely people in this room who have better ideas about this topic than I've seen yet. And I really want to hear them. That's part of the reason I wanted to do this talk. So I saved a lot of time for questions at the end, and I really hope to hear some great questions, and yes, even statements. I'm going there. So just a quick outline of what I'm going to talk about. I'm going to throw out some definitions. I'm going to talk about network interfaces as we sort of traditionally learn them in this kind of imperative style. I'm going to talk about interfaces as module types in OCaml. I'm going to talk about kind of a grab bag of nice things to have. And then I have some time for questions after that. So first off, what I mean when I say non-imperative. I run in circles that kind of throw the term declarative around a lot. But this is really what I'm trying to get at, is interfaces and code that fulfill these properties. They're independent, they're stateless, and they're deterministic. We're going to examine some approaches that are more declarative than the network programming paradigms that we traditionally teach in systems classes, but we're not going to get all the way to a working interface that unambiguously fulfills all of those criteria. So sorry if that's what you're here for. You can, there's no tables to table flip, but you could probably like flip a chair and run out. And what I mean when I say network programming is the part of your code that is concerned with sending messages to and receiving from programs running on other computers on the other end of like greater than one network link. I'm talking about the layers of abstraction that we use to send messages between computers over potentially lossy network links. Most of the time when we're doing application programming, we don't get to think about like the full depth of this stack. We often say full stack, and we mean like a client to a server on layer 8. We have this kind of this level of abstraction presented to us because the operating system represents the network to us at this layer of abstraction. I should also mention, since I'm talking about messages and links, that I am not qualified to talk about distributed systems. So there will be no photographs of anything on fire during this talk. Yeah, sorry. Sorry, not sorry, I guess. So first off, network interfaces as we learn them, or as I learned them. I guess I shouldn't include you all in my personal past experience. So traditional operating systems kind of want to handle like a large part of networking for you. The application's access to the network is mediated by the operating system and the API that it chooses to present to the application. Most of the time, that's the sockets API, which I've helpfully labeled sockets in this nice little diagram here. Ooh. So by accessing the sockets API, the application can request that some stuff happens in the kernel to get data out onto the network hardware and onto the wire. There's not really another choice in doing this in Unix for the most part. Like you can put stuff on top of it, but you can't get under it. If you're doing network programming in a Unixy environment, at some point it's probably going through there. The sockets API was originally designed for C, but like most languages have their own interfaces for it, and the interfaces look really C-like. So let's have a really quick look at the OCaml implementation of sockets and see whether the functions that we see look like they might be something that's independent, stateless, or deterministic. So this is a little selection from the OCaml Unix library, which implements a whole bunch of socket stuff in addition to a lot of variants like ebad file descriptor. This connect isn't really very declarative, is it? It does a side effecting operation on the file descriptor that we pass in. So actually, let me back up and talk a little bit about socket for a minute. So when we look at socket, what socket is doing is taking some description of 3 things that we're asking for in our description of how we're going to connect to the network with this socket. And then it's going to give us back a file descriptor. So we need to tell it, like, what kind of network do we want to connect to? Is it IPv4, IPv6? Is it some Unix thing that's pretending to be an IP network? Do we want reliable transport, or do we want like faster but like not as reliable transport? Do we need to disambiguate that protocol because those first two things weren't enough to tell the thing what we wanted? And once we've gotten all that right, we're going to get something back that looks like a file on a file system that we can hopefully do some interesting stuff with. And then connect is our interface to actually turn that into something that we can send packets to and hopefully have them go down the wire off to someone else. You'll notice that the return type of socket is unit. The return type of connect is unit. Connect is side effecting, and it is not really possible to know if you just have a file descriptor without any other information, whether it's currently set up for you to send network stuff across it. Like none of the difference between like a socket that's been set up and hasn't been set up is represented in the type system at all in this interface. Oh, I should also mention that connect is a really error-prone function as well, and this particular one just will throw an exception and you'll be sad. Because it happens very frequently that you run connect and you're like, I'm going to connect to my best friend, another server, and the other server goes, I'm sleeping, bro. And this is where you find out and your program blows up and you're not a happy person. So, but it's also worth noting that this is pretty much all of the specification that we did of how we were going to interact with the network over the course of this socket's lifetime. We can set a few more flags when we do particular things, but pretty much these are our specs. And they're really not very precise. This is just a rehash of what's actually going on there. But there's a whole lot more possibilities for the state that's represented by the operating system's choices about the network that we really haven't had any input into. So this command is sysctlnet. On a Unix machine, it will give you a list of all of the tunable network parameters that you can access through proc. On my machine, there are 688, which is way more than 3, and even way more than 8, and even like way more than 10. Like it's a lot. And it's possible that you might even care about some of them in your application. Like for example, this particular setting is the setting for the maximum number of allowable waiting connections in TCP. And so you can imagine like you're running a big web server that wants to take a lot of connections, or you're running a load balancer. You care about the value of this thing, unfortunately for you. So if you're running an application that cares about this application is always going to care about that. That's not going to stop because the machine rebooted or something happened to change the state of the environment that your application is running in. The property that you care about that is inherent to the thing that you're trying to get done. We have a lot of DevOps tools for attempting to make the values of settings like this consistent over time and over multiple machines. They're all essentially out-of-band updates which take place like outside of the application. My application code, it wants that state, and maybe it even wants to set that state, but it doesn't necessarily have an in-band way to demand it, and it might even not have a nice interface for making sure that it's set. So implicit state, I don't like it. So I'm going to go on and talk a little bit about interfaces as module types and how I think we can build better interfaces. So what if we could choose or even make our own abstractions for how to access the network? We could make whatever we wanted be implicit or implicit. We could have whatever knobs we wanted to tune be exposed. We could, if we wanted to, make libraries that just return pictures of cats all the time, because that's really all we want to do anyway. So how can we get to this beautiful future? Some of you have been spoiled on this. The answer is unikernels. So in a traditional operating system architecture, you write your code, you compile it for an operating system, you run it on an operating system that's probably running on some virtualized hardware if you're deploying it in production or in a cloud. In a unikernel setup, what you do is you write your code, you compile your code, and your code becomes an operating system that you can then run on virtualized hardware. And this means that instead of having the traditional operating system interface standing between your application and what you can do with network hardware, you can potentially have direct access to that through whatever kind of libraries you want to link in. So you'll note, so this is just sort of a diagram of the things that you might have linked into a unikernel application that is running on a network. So you have your application code that you've run, and you're very proud of it, and you want it to go out into the world and succeed and be happy. You might have a library that provides what we call the transport layer, so either reliable or unreliable communication over a network in datagrams. You might have a network layer library, so that's IPv4 or IPv6, generally. Something that understands how to handle whatever layer is below that, usually Ethernet or possibly Wi-Fi, although that would be a bit strange. And then something that knows how to talk to whatever virtual network hardware you've been provided by, excuse me, oh, that was loud, that you've been provided by the environment in which you're trying to get your unikernel up and running. And then finally, all of that is going to be running over a language runtime. So instead of running like memory unsafe code, in the unikernel environments that I have some experience in, you have the excellent benefit of having a runtime that knows how to keep you from shooting yourself in the foot when you are parsing input off the wire from random people that you don't know. So if we're going to talk about replacing the monolithic structure of sockets with something that is more decomposable and something that we can sort of interact with a little bit more and maybe involve ourselves a little bit more in, it's useful to impose maybe some structure on how these libraries express themselves. Because if we just say, you can have a transport layer library, and I really want my application code to interact with it in this way, but the network, like whatever's beneath it, it's going to have to interact with it in this like different other way because I just kind of felt differently that day. You're going to have a bad time when you try to go and compose all of these things. So you need to impose some kind of rules. The unikernel system that I have experience in is called MirageOS, and it's written in OCaml. And the way that we deal with this problem in OCaml is all of these libraries are modules. And in OCaml, modules are allowed to have module types. So for example, if I want to make sure that I can easily swap my IPv4 library with an IPv6 library, or my IPv4 module with an IPv6 module, I'm sorry to use those terms interchangeably, but in this case, there's no loss of meaning in doing that. I can then define module types for IPv4 and IPv6 so that I have a stringent set of rules for what IPv4 and IPv6 mean and do in the context of this unikernel operating system. I can then figure out the commonality between these two things and make another module type for just IP. And I can write interfaces for the link layer and for the transport layer that speak in terms of IP. Oops. So I just wanted to show you a few of the module types that we have that I work with a lot of the time when I'm building unikernels in MirageOS. So if you're familiar with doing, if you've done any kind of stack programming before, these things are not super new to you. So as I mentioned, we have module types for IPv4 and IPv6, and then a super type for IPv4 and IPv6. There are also some module types that don't directly correspond to any particular layer. The nice thing, because these module types can be included in one another, you can build nice little atoms for things that you want to be represented in all sorts of things. So for example, we have a module type flow for connections between endpoints, which is useful for both in a network context of you have a machine that wants to talk to another machine over the network. And it's useful in the context of you have a machine that wants to talk to another machine over shared memory, like for example, through the hypervisor. The other thing that I wanted to note is because I did touch on this, but I want to make it really clear that because we're defining these things in terms of module types, we can have separate implementations that make different decisions that fulfill these module types, and then they're interchangeable within our system. So if I decide that I have a really strong feeling about which TCP congestion control algorithm I want to use, I can just swap whatever one I want in there. So does this actually look not imperative when you look at it? Well, let's look at some more type signatures before we make any decisions. So this is the module type signature for flow. We have a type parameter for basically doing side effecting operations that we might want to yield for. because we're doing this is in a cooperative multi-threading environment, so you have to be explicit about when you're yielding and when you wish not to do that in your sequencing. We have a type that's basically a type for a big wad of memory, the fundamental building block of doing stupid stuff with networks. We have an abstract type for our flow, which is the thing that these modules will be implementing and speaking in terms of. And we have an error type because that's just always kind of a good idea. So we have also some expected primitives. We can read our flows and we can either get some memory, yay, or discover that that someone else has closed the connection, no, boo, we're sad. Something even worse happened, we're even sadder. And the same thing pretty much for write. I should probably be a little bit clearer about this, just in case there are somehow people who haven't ever programmed in OCaml in the room. I don't know how that would ever happen, but so what's happening here with this type signature is this is a polymorph. This is a tag. It's basically just a marker on some more data or another type that says I want to address this as being okay. It's very reassuring. Another one that's EOF and another one that's error, and then this type is one of those three things. And then the of something is the thing that's attached to this OK tag is some data that I might actually be able to do something with. Same with the error, hopefully. So you might have noticed that there's actually no way to create a flow in that module. That's actually a pretty complete representation of what's in the flow module, and there's a pretty obvious thing missing. Everything is in terms of a flow, but you have no way to get one. One of the ways that you can get one is actually in a different module type, in an implementation of a different module type, so some implementation of this TCP module type. Part of the required signature for TCP things is this function create a connection with some TCP implementation to some IP address and port. And then if everything went OK, give me a flow that I can use to communicate with it. And if things went badly, give me an error. So OK, that's all fun and games. How do we actually run a server? How do we compose this and do something with it? So there's something else that module type TCP defines that you would probably expect for something that wants to both send and receive data. We define a callback, which is just a function that goes from flow to unit IO. So a side effecting operation, yeah, sorry. And we define also an input function. There's a little bit of commenting down here, which I think might be a little bit hard to read because of the color. I apologize for that. But this input function just takes a TCP implementation and then a function from int to callback option, which is basically you just write a function that matches on the port number and says, OK, if this is a port number on which I have on which I want to do something, return that thing that I want to do. If it's a port number in which I'm not interested, return none. So the TCP implementation will then say if it gets none, it will just send a reset packet and not open a connection. If it has some callback that it knows what to do with, it will initiate that connection, and the callback will run with will start running with the value of the flow from the incoming data connection. So we can define a function and then just use it. Yay. So this is a fairly trivial server, which just basically just opens a service, keeps reading a whole bunch of data, and then discards it. If you're a fan of old RFCs or blog posts about old RFCs, this is the I can't remember the RFC number, but it is the standard service on port 9. So this is a very succinct implementation. The only thing that's missing is the I've elided report and close, which I hope doesn't confuse anyone, but it does exactly what it sounds like. It just complains about the error and then closes the connection. So what we have defined here is a recursive discard function that will just keep, whenever it is running, it will continually try to read this flow. And the operation there is a bind operator on the threading library that we're using. So basically, you can imagine that it's basically sequencing. So we wait until we've found a way to read the flow and we get a result. We figure out what the result was. If something bad happened, we report and we close. If we got OK in some data, we don't care what our data is. We're just going to throw it away. And then we're going to go back and do it all over again. So this fulfills our type signature of flow to unit IO. So this is eligible to be eventually shoved into our input function. So this abstraction down below with the s.listen and s.listen TCP v4 is a little bit of syntactic sugar for how to set up those input functions. I'll show you the longer way later, but just for brevity's sake, I wanted to show you the sort of sugared version here. It's very frequently the case we've discovered in Mirage that what you want is some representation of all of the standard things in a stack. So we have a module type stack before that provides all of those things bundled together in yet another module. This is sort of a theme in OCaml and MirageOS that if you have a problem and you think a module might kind of maybe be a solution, just go for that, just do it. So this is what it looks like when you build the whole stack explicitly. Basically what you do is you are building your own module with some module arguments. In OCaml we call this a functor. I'm sorry that we call it a functor. Haskell people, they didn't ask me. It has some explicit inputs which are in the form of this is the actual implementation of the module and then colon and the module type. So we have something that represents a console. We have something that represents a network. And by network, we mean really low level, a virtualized hardware support network. We have something that represents a clock, and then something that represents a way to get random numbers. So given our network, we call an Ethernet interface, and we say, OK, build me an Ethernet module given what you know about this network. And OK, now we have Ethernet, and we can send Ethernet layer messages, and that's great. But we want more. So since we know that we're going for IPv4, we need ARP. Sorry, everybody. ARP is a glue layer between IPv4 and Ethernet, and the less you know about it, the happier you are. So that you can be content that you know enough about it right now, that it needs some stuff, and it looks like it's stateful, and that's really sad. But given that, once we have that, we can get an IPv4 module, which we could actually use to send messages that someone might care about. So that's great. UDP is also pretty simple. We can just build it on top of IP. TCP is quite a bit more complicated. It has timers. It needs to know how long to sleep for. It needs to generate random numbers. It has all kinds of needs, but we have satisfied all of those needs right here in this call. And if we're in the situation where we want to be dynamically assigned an IP through the DHCP interface, which runs over UDP, we also have to build this slightly hungry module out of our console, a time implementation, random, and UDP. So the reason that I'm talking about all this is that I really love the explicitness of the way that this is built. You can see at every single layer, it's clear what you'll be calling out to. And because of the module types, it's clear what you're providing. So OK, that's really cool, I think, personally. I don't know how you feel about it. But is it any more declarative? Is it actually any less imperative to build your networks this way? So here's my argument for why I think it is. The layers of our stack, as I said, are explicit and they're deliberate. Which seems to me to give us some major determinism points. We can build our applications in terms of pure functions over inputs, even if we have specific APIs that don't do that right now. We can build different APIs. We have the power. We can define functions to process this data without all of the implicit external dependencies of our 688 things that were in proc. And to me, that seems like major plus independence points. So I'm going to talk a little bit now about nice things to have. So when we have an interface to a network that is presented as this fully virtualizable thing, where we just have a module that fulfills a module type, there's no reason that we can't actually make our own implementation of a network, even like something that maybe is in memory only, or saves everything before it sends it to the network. Like, congratulations, you invented TCP dump, great job. Or something that drops 15% of your traffic, or mangles your message in semantically interesting ways, or has huge latency but is really unpredictable, or responds to all your messages with a ping flood, or does any one of the horrible things that happen to machines on networks all the time, but in a way that you can control and assign and do predictably. So this is so valuable for testing. We get the question a lot, how do you debug a unikernel? And pretty much that's how you debug a unikernel. So there's implications for this explicitness in things besides the network as well. So we passed a random number generator. So we can pass whatever random number generator we want, including constant 4, which is useful for again useful for testing, and also useful for debugging if you want to remove some of the intentional stochasticness from the environment. This is a really useful thing to be able to do. And same goes for clocks, especially in networks. Same goes for clocks. It's really nice to be able to pass something a fast clock or a slow clock, or a clock that sometimes goes back in time and messes everything up. This is a really fantastic way to find bugs in your application code and all your other code and all of everybody's code ever. I recommend it highly. So I wanted to give you a quick look. This is just what that looks like. It looks exactly like the stacks that we were building before. We just put some different stuff in there. So this particular one is Mirage vNetif, which is a virtual network interface. This is like a shared backend, so we can plug multiple virtual network interfaces into the same bridge, and then they can talk to each other over a lossy link or a link that only sends cat pictures or whatever. One of which is this lossy netif. And then we just build our stuff on top of it as normal, or we substitute in some fast clocks because we're trying to do some debugging on aging out of our ARP cache. So we want to make time go 10 million times faster so we don't have to wait on Travis for 5 minutes. And we can combine this with property-based testings to see really interesting things, like, for example, whether putting 2 of our nodes on these lossy links together means that for some reason we do something wrong in our TCP state machine. So I have another neat thing from the neat things grab bag that I wanted to talk about. I kind of tried to skate by it as quickly as I could, but it's probably fairly clear that a lot of the interfaces that I'm talking about for specific implementations of these network layers, or maybe I did pull too fast on one and it wasn't very clear, but a lot of these interfaces are side effecting. And that means that we have data structures that we can't really make guarantees on the past of, and we don't necessarily have good ways of imagining what's going on with them in terms of their current state and their past state and inputs. We just sort of lose the ability to reason nicely about that. And in the situation where you really genuinely do have to have multiple control paths into something in order to update it, this is pretty hard to deal with. So I'm sorry to tell you more about ARP. I told you you'd be happier if you didn't know. But I'm going to tell you a little bit more about ARP anyway, and I'm just going to apologize ahead of time. But I have to forward a few slides first, sorry. And I have to get my focus in the right place. Why are computers so hard? Oh. OK, so I'll just tell you about it. So this is a way of mapping. It's a way of mapping IP addresses to link layer addresses, and it also has an expiration time attached to it. The intention is that you have a whole bunch of nodes that are joining a network. They don't necessarily know what their IP addresses are, but they have a burned-in link layer address that they always know. And so you have to have some way for these machines to discover what each other's numbers are, which means that the machines have to know what their numbers are, and they have to be able to tell the other machines on the network. That's what ARP is. Basically, imagine it as just a key value store with an expiration date attached, which is a super, super common structure in these like really small bits of state that we see in the network stack. But there are three possible things that you can imagine happening in terms of threads in ARP. So you might be responding to an incoming message that says like, hey, bro, my name is 192.168.3.50. I'm at MAC address Q. Let's be buds. And your ARP cache goes, oh, yeah, OK, I totally want to be buds. This is going to be great. Or you might have an incoming request from something farther up the stack that says, I really need to send a message to 192.168.3.50. Do you know where that is? And the ARP cache says, I got this. It's fine. And then you also have the influence of time on the cache, where you knew where someone lived, but they've gone away. And this information is gone, and you have to let go of it, and you have to move on with your life. Needing to do all three of those things at once is a bit difficult. So it's useful to have ridiculously powerful distributed data stores that you can use to do that. Ermin is a library basically for persistent storage. You can do snapshotting, branching, and reverting in it. You can basically imagine it as an interface to Git, but for your data store. And you can, the really nice thing about it is that you can deal with the stuff that you're putting in the data stores in a type-aware way, which has the implication that you can write custom merge functions that know what your types are. So when you update stuff in Ermin, you do it in this kind of like traditional Git way. You clone, you edit, you try to merge back. But you don't get this, because Ermin knows the types of, Ermin is smarter than this merge algorithm. And it knows, for example, that if you have two changes that are not mutually exclusive, you should be able to merge them, or you can tell it that. So for example, in the case of ARP, I don't have the slide, but in the case of ARP, we have the very useful property that the only way that we ever remove a node is if it's expired, and we have a date for expiry for it. So we can write a really simple merge function that says, always prefer something to nothing, and always prefer something with a later date to an earlier date, which means that we can trivially put all of this information into Ermin and then basically get a Git trace of our ARP cache. And the other nice thing about it is that it provides a whole lot of backends, so you can run it in memory, and it's not ridiculously slow. And then in testing, you can just flip this. Basically, you can flip what module you call it with, and suddenly it's on disk, and you can see persisting in memory all of the changes that it's made. This is a really useful thing for managing the situation where you, of necessity, have mutable state, and you don't want to, and you're trying to figure out how you can live in this awful world that you and everyone else around you have created for you. That's all I've got, which is good because I'm almost out of time, but I would appreciate any questions or statements that you have. Thank you for your attention.